5 or 6. Okay. So now we will continue with the normal multivariate normal distribution. So recall that since we can only assume at this moment that the covariance of your random vector y is non-negative definite, so we will be working on the moment generating function so that we can have some properties of this, the distribution of your random variable. Because if we have a known continuous probability distribution of y, then we are assured that the covariance of y is positive definite. And if that is positive definite, then the covariance of y, which is also denoted by sigma in the notation, the inverse of this covariance exists, because if this is assured, then we know that sigma will be invertible and the inverse exists. For the meantime, if this is the only assumption that we have, that it's non-negative definite, then we can work on the moment generating function to describe the properties of the distribution of your random variable. So now we will work on moment generating function for a normal distribution. So the normal distribution is usually derived by assuming first. So this is an illustration of how normal distribution is usually derived. We assume first that we have a random variables z1 to zn, which are independent. And each of the zi here is a standard normal. No? So it has a mean 0 and a variance 1. So each of them, this is z sub I. No? Each of the zi's in this vector is standard normal. So since it is standard normal, then the expectation of z will be equal to 0. So if we get the expectation of this, so the expectation of z1, the vector z1, z2 to zn, which is equal to the expectation, the vector of its expectations for each, no? So z1, z2 to expectation of zn, but each of them is 0. So what you will have is the mean vector there will be equal to the 0 vector. It's not just a single 0, but it's a vector of 0. Okay, so this notation here is actually a vector of 0, because each of the zi's will be 0, and each of them will have variance equal to 1. So the covariance of z will be equal to the identity matrix, wherein all diagonal entries there are 0 and the off diagonals are equal to 1. So independence will assure us that covariances between zi and z, the covariances of zi and zj will be equal to 0. Or in notation, you have z is normally distributed with a mean vector 0 and covariance matrix I. Now, recall that the moment generating function for a standard normal, so this is a standard normal, z is equal to the product of e to the ti squared over 2. So this is kada z manino, because this is z1, z2 to zn. So the product there means for independence. So kada isa sa ilaha, kada zi kada zi is normal, and if it is standard normal, then it is equal to square over the moment generating function for a standard normal, and then the product becomes summation because e to the a times e to the b times e to the c, or dili ta mo gamit anang abc, say x1, x2, x3 will be equal to e to the summation of xi I from 1 to 3, for example, in this particular scenario. So, ibig sabihin, when you get the product here, that will just be equal to the sum of the ti's I from 1 to n in general. But summation of ti's is actually in vector notation can be written as t prime t. So if you have t prime, t1, t2 to tn, this is t prime, and then this is t1, t2, tn. So this will become t1 squared plus t2 squared and so on and so forth until tn squared, or that is the summation of ti squared I from 1 to n. So this is actually your t prime, no? T prime t. So summation of ti squared can be written in terms of vector form as t prime t. So the moment generating function for a standard normal distribution is equal to this. So the moment generating function with where z is standard normal is equal to e to the exponential of 1/2 of t prime t. Okay, so remember that. Okay, a result is we have suppose mu is an n by 1 vector and A is an n by n matrix. So we define a transformation, say y is equal to az plus mu. So z here is normally distributed, no? Mean vector 0 and covariance matrix I. So if we transform a normal, if we transform a standard normal to az plus mu, your y is still normal, but we will look now on its parameter. Okay, what will be the parameter of y when we transform z as az plus mu? It says here in this theorem, it's still normal. Later you will see that it's still normal, but the mean vector will be equal to mu, so equal to this constant here. And the covariance matrix of y will be AA prime.